slide takes a look at some case studies compiled by ETS Labs. Specifically, what they look at is the impact of winemaking on the growth of spoilage microbes in juice, primary fermentation, barrel aging, and bottling. And so looking at this particular case, an ETS client that had a problem in which the wines developed high levels of ethyl acetate, which again imparts sort of a nail polish remover type flavor and aroma. And it's typically caused by things like acetic acid bacteria and certain kinds of wild yeasts. Their native fermentation started fine, but then became sluggish or stuck. And so they had ETS Labs perform a chemistry analysis and a microbiological analysis using scorpions. And so the chemical analysis is over here on the left, and I highlighted some of the important things, first of which is looking at the nitrogen levels. So yeast assimilable nitrogen, or YAN, was a little bit low. YAN is a reflection of both the alpha amino nitrogen, or NOPA as it's called, and ammonia. And alpha amino nitrogen is really just the primary amino acids that are usable by yeast. It doesn't consider the proline content because yeasts don't typically use the amino acid proline, but that it also considers the ammonia content, which again is a very simple form of nitrogen for the yeasts. And together, these guys roughly equal the YAN. But YAN is a little low in this particular case. The suggested YAN should probably be somewhere between 150 and 400 milligrams per liter. So this low YAN is a bit of a risk. Basically, it creates a risk for non-native microbes to sort of overgrow the desired microbes, if you will. The weeds can kind of handle that lower nitrogen and could potentially outgrow your primaries. And so in this particular case, it's right in the middle of a cold soak. And so, the numbers would vary depending on whether you're at the beginning of the cold soak or the end. But this is right in the middle. And so the main thing to pay attention to here, at least from the chemistry, was the low YAN. And then over here on the right, you're looking at an array of microorganisms, and by far the most startling is this 417,800 cells per milliliter of Hansennia spora, this spoilage yeast, which is known to produce ethyl acetate. So there's a predictable problem due to the elevated levels of Hansennia spora and low YAN. So again, Hansennia spora was able to grow in the presence of low nitrogen, outcompete the primary, and produce this undesirable end product. And so then, again, some of the preventative checks, obviously using a commercial yeast strain with strong fermentation traits, it's not going to let you down if YAN levels get a little too low, for example. And of course, supplementation. Once you know the chemistry is a little bit off, you can always supplement with diammonium phosphate or something just to get the nitrogen levels up to give your primary fermenters a bit of a head start. So in this particular case, there was a high Brix juice, and the juice had an elevated pH, which is a problem. And the client had rapid and excessive VA production at the end of primary. So that's key. This is the end of a primary fermentation, high Brix juice, and it's the fermentation is being conducted at a relatively elevated pH. And so here's the data set right here. And so a couple things to look at. I pointed them out, but the pH, like I said, is pretty darn high. Here's the first sampling, second sampling, third sampling. And again, the pH is pretty darn high. Your usual is like 3.4 or something in that ballpark. Notice the volatile acidity gradually increasing. This is the key right here, though. Malic acid is being depleted with each sampling, and right there you should get a general sense of what's happening just by looking at that. And obviously you can see that the sugar is being consumed. And so another thing to notice is that the molecular SO2, and I didn't highlight this, but molecular SO2 is way low. You need something around 0.8 mg per liter, for example, to be antimicrobial. And so you've essentially lost your molecular SO2. effectiveness, and you've got these interesting things happening in the chemistry. And so, not surprising when you look at the microbiological panel here, the Enococcus is massively expanding from first sample to the third sampling. I mean, millions of cells per milliliter. Now, obviously, there's some other VA producers as well that are increasing, but these numbers are so minuscule. The lactobacillus and the acetic acid bacteria are pretty small, but by far, what is clearly happening here is you're getting a wild Enococcus. Remember, this is right at the end of primary, so you haven't even initiated malolactic yet. And so again, the sort of suggested what's happening kind of information is native Enococcus strains are consuming fructose, for example. That's and because the pH is a little bit high and permissive, they can produce significant amounts of VA or acetic acid. So again, some of the preventative actions are obviously to monitor levels of malic acid and certainly checking for the presence of heterofermentatives is ideal, and reducing the bacterial load for sure. Obviously, sulfiting is something that needs to happen, and stabilizing against further growth. Obviously, adjusting the pH, and then if necessary, restarting the primary. So again, you can add nutrients and fresh yeast or any number of methods that a particular winery uses, but restarting the primary might be necessary. Here's some examples of, or an example, a case study of problems in the barrel. In this particular case, a client had difficulty managing molecular SO2 levels in the barrel. And so the result was elevated levels of both VA and ethyl acetate in the barrel. And so again, you can take a look at the wine chemistry as well as the microbiology. And so it shouldn't be surprising here. You can see it starts over here. So the first sampling is here, December 2013, and then there's 2 additional samplings thereafter. And so pH is relatively high, but VA is gradually rising. In addition, you see molecular SO2 hovering well below what's antimicrobial. But the kicker here, again, is the massive rise in ethyl acetate corresponding with the rise in volatile acidity. And so and this shouldn't surprise you then. In this particular case, in the barrel, massive increases in acetic acid bacteria. These are microbes that definitely need a bit of oxygen in order to proliferate, and so that tells you that there's obviously some issues, particularly properly managing the headspace in your barrels. And so if we take a look at this, elevated levels of acetic acid bacteria in the juice can stay with the wine throughout the winemaking process. They're difficult to control at higher pHs. So again, some of the preventative actions, as I mentioned, aggressively managing the headspace, because you don't want these organisms to have that, roughly 50% atmospheric oxygen content before they can, start converting ethanol to acetic acid. The and obviously the effective barrel cleaning and sanitation to reduce acetic acid bacteria in the barrel, and other things too. Even before all this, you can sometimes these things are associated with picking overripe fruit, for example, which is a big issue. And then even downstream of that, like in the bottle, bottling wines that contain pretty high dissolved oxygen is a potential risk. If you're carrying over acetic acid bacteria from the barrel to bottling, obviously you can have a problem there. So you want to bottle at less than, say, 1 part per million of dissolved oxygen, and even 0.5 or less is probably ideal. So you can prevent these acetic acid bacteria from doing any of these weird late blooms.